This morning in the seminar, and I recorded it and I just got it up online in the last half hour or so, what we did was we did a review of the general procedure. I guess I'll talk about it briefly here again. When you're trying to optimize or maximize some quantity, you need to come up with an equation that connects that quantity or relates that quantity that's to be maximized or minimized to another variable. And sometimes the best you can do to begin with is to come up with an equation that can be used to calculate that quantity in terms of two different variables. But what you do then is you use what's called an equation of constraint to remove one of the variables. Anyway, once you get that formula for the variable, which is O in my illustration here, defined in terms of x, then you find dO dx, you identify the critical number, and then you use that critical number to answer the question. Maybe the question is just saying, what is the critical number? What should you charge for a ticket to maximize the revenue? Or maybe the question is, what is the maximum revenue? Anyway, then what we did was we went over number 5, where we had, and this was one that I had set up yesterday, but we just had to finish the procedure. When we found the derivative, it's almost at the bottom of the screen on the right-hand screen. The derivative was 2s minus 16,000 s to the negative 2. You factor it, you identify the critical numbers, and the only two critical numbers were 20 and 0, and we throw 0 out because it just doesn't fit in terms of what we're trying to do. S is the length of the side of a square. Then what we did was we did number 6, which is the same basic idea as example 1 or warm-up 1. I don't remember what I called it in the lesson. Except that in the lesson we started off with a piece of material, I don't know whether it was metal or cardboard, it doesn't matter, that was rectangular. In this case, we're starting off with something that is square. And we ended up removing a square of side length x from each corner, leaving us with a box when you fold up the sides or flaps that was 3 minus 2x by 3 minus 2x by x. And when you multiply those together, you get the volume. And I knew I was going to run out of time this morning, so where I ended up was here, and I said what I would do is multiply this out, then differentiate it, and then solve it. Is there anybody who would like me to finish this problem? Okay, yeah, might as well. So right near the end of the class, Naya, and I don't know, it was you, we had a couple of people say, could we just not expand it out and use the product rule and the chain rule? And I said yes, but I'm more comfortable expanding it out as a teacher explaining this to everybody. So v would be equal to 9 minus 12x plus 4x squared times x. So I've done a little bit of FOIL with 3 minus 2x times 3 minus 2x. And as I'm speaking, and I'm just double checking and it looks fine, when I multiply that all by x, I get v equals 4x squared. Sorry, I get v equals 4x cubed. By the way, JV, did you finish this question? Okay, I'm just checking. So 4x cubed minus 12x squared plus 9x. And I've swapped the order of the terms because I just like highest degree to lowest degree. I think that looks okay. So when you differentiate this, you get dv dx is equal to 12x squared minus 24x plus 9. Just double checking that. That's interesting that there happens to be a common factor of 3. I'm not quite sure if that's always going to be the case, that there will be a common factor here. I suspect it might be because the length and the width before we cut out the x's both had a 3 in them somewhere, I suspect. Anyway, I can factor out that 3 to just make my solution work a little bit easier. 3 times 4 is 12. 3 times negative 8 is negative 24. 3 times 3 is 9. Okay, so now I've said to you, everybody, many times, I don't really like the idea of doing this. I don't like the idea of saying derivative equals 0. There's nothing technically wrong with it, but it creates some issues, educationally speaking, from my standpoint of teaching things. So what I would rather you do is look at this derivative and say the only factor that contains an x is this factor. So the question is, where is it equal to 0? And I understand that you probably look at that and say, what's the big deal? What's the difference between writing that and saying dy dx equals 0? Again, I've mentioned this before. If you commit yourself to this, then mathematically, looking at this, there's nothing wrong with getting rid of this 3 because you can divide both sides by 3. But 3 is part of the derivative. You shouldn't do that. So it's a idiosyncrasy of mine that I just don't like doing that. Can we do our b squared minus 4ac calculation here for me, please? I'm calculating b squared minus 4ac to determine if it's factorable, because if it is, then it's easier. And it is. Wow. That's unusual. I wonder if because it was square, that's why it's factorable. You might want to try that with other ones. It's very unusual for these folding flap box questions to be factorable as a derivative. B squared minus 4ac is 16. Is that what it works out to? So 16 is a perfect square. This is factorable. Okay. We're going to have 3 times, and just, be patient. I have my own way of factoring. I know some of you can look at this and tell me exactly what it is. I would immediately try 2x and 2x and 3 and 1, and they would have to both be negative, and it happens to work. Okay. If it didn't work, then I would try 4x and x. And by the way, when I say it happens to work, that's because if I FOIL it out, I get that middle term of negative 8x. So I guess I should be factoring it over here. 2x minus 3. See, I put that equals 0, and I got trapped in equals 0 with the derivative, and it's not. And then 2x minus 1. So x equals 3 over 2. X equals 1 over 2. So the two mathematical solutions are x equals 1.5 meters and x equals 0.5 meters. So to finish the question, we have to, could a first derivative chart right now clear up the confusion as to which of those two is correct? Yes, it probably could. But I'm always going to suggest or recommend you look at the context of the question. You look at the domain of the critical variable, and you throw out any numbers that are not in the domain. And the domain here for this situation, if I go back and look at the diagram, the domain will be that x has to be between 0 and 1.5. It has to be greater than 0, right? You can't have nothing cut out, because then you're just sitting there looking at a flat sheet of paper that's two-dimensional. It's not a box. And you cannot reach 1.5 either. This is the domain I'm referring to right here. You cannot reach a cutout size of 1.5, because if you cut out 1.5 from both sides of 3, then you're left with nothing. In other words, if you put 1.5 in here for x in the volume, you get 0. You're going to get 0 for a volume, which is not a maximum volume. So anyway, JV, the correct critical value is the only one left, which is 0.5 meters. So what are the dimensions? Or what were we asked? What's the largest volume? Okay, we don't even really care about the dimensions. We want to know the largest volume. So you're going to put 0.5 into a volume equation. And you could put it in to any one of these three. I mean, I think it's probably easier just to put it here in the factored form. 3 minus 2 times a half is 1. No, 3 minus 2 times a half is 2. 2 times a half is 1. 3 minus 1 is 2. So I get 2 times a half, which is 2. So 2 cubic meters is the maximum volume. Is that okay? Perfect. All right, before we move on and look at the other examples, does anybody have any other questions from, yeah, 7? Okay. Oh, 7b. So I had talked about this one, right? I love the diagrams in this book. Let me just, we know what's going on here. You're building a rectangular area where you have the beach front that doesn't need to be roped off. I mean, you don't want it to be roped off because then people can't go into the swimming area. So what we have for, I'm going to draw it with straight lines, although this stuff is going to be floating around and changing shape. You have this situation, which I would probably label this as W, this as W, and this as L. And I know that you're asking about B, but with question A, you would have an equation of constraint. And again, EOC is just my abbreviation. It's not something that everybody would recognize. The equation of constraint would be 2W plus L equals 400. Can I ask you, Arden, is that what you did? So you used L and W, okay. And at some point, because you're dealing with area, area has to be equal to length times width. There's too many variables, so you rearrange your equation of constraint and get negative 2W plus 400. And I am going to go through A because I think there's some value in it because it connects, I believe, to B, if what I'm thinking is correct. So we end up with A equals the length, which is negative 2W plus 400. Times the width, which is W, and we end up with A equals negative 2W squared plus 400W. And let's just pretend we're working on A right now. Okay. So now we differentiate that, and this is really nice actually, everybody, because it's a quadratic function defining what we want to optimize. The derivative is going to be linear, so solving a linear equal to 0 is pretty basic. The derivative here, dA dW, will be equal to negative 4W plus 400. If you want to be really slick about it, you're not even really solving an equation. What you're doing is factoring, and I can factor out a negative 4 and get W minus 100. So it's pretty clear without actually saying equals 0, the critical value of W is 100. And that leads you to the answer to A. The answer to A is going to be, the maximum area will be when you have, so A is the green stuff, 100 and 100, and I guess that leaves 200 here. Am I right? Okay. So now what do we do with B? With B, the fact of the matter is, the work is going to all be the same, isn't it? I mean, just because you have some limitation on what W is doesn't mean the area isn't still calculated that way. So you get down here and you look at this and you say for B, this is for A, for B, you're looking at the derivative, you're saying the critical value of W is 100, but then you have to throw it out. And then you maybe get caught by saying, well, how am I supposed to answer the question? I love, there's so many times in this course where I say this, I love that math doesn't lie. We always say there's exceptions, but when it comes down to the rules, there really aren't in math. There is another critical value of W here. It's 50. Because that's where the function ends. I mean, we don't necessarily need to think of this as a function in terms of W being an X coordinate, but that's what it is. So we have another critical value of X of 50. And we're left with one critical value. I said of X, but it's of W. And that must mean that in order to maximize the area, if the condition is W has to be, what this is saying, I want to be very clear here. When you really unpack this, this is saying W has to be less than or equal to 50. By saying it can't be more than 50, you're saying it can be equal to 50 or less than 50. So this function in B has a domain of that, which means since the function ends at 50, this is what I meant by saying I like this. It ends at 50, the derivative is not defined at 50 because there's no other side to that point, which means it's critical. By the way, 0 is not a critical value because it's not where the function starts. And we've had this conversation before. The function starts infinitely close to 0, but we can't put a number on where it starts. If you wanted to, what you could do, and maybe I will do this, is let's do a first derivative chart for part B. Well, for part B, our first derivative chart, I think I can squeeze it in here, would go from 0 to 50. That would be it. That would be the only interval. The only critical value happens to be the end of the function. So up top we can put -4 and W minus 100. So -4 is negative, W minus 100 is negative. What does that mean? It means that dA dW is positive. What does that mean? It means the area is increasing over that interval. So if it's increasing everywhere from 0 to 50, then it must max out at 50. Anyway, is that okay? Okay. You're going to see a couple more problems, and after we're done with today's lesson, I'll point out to you which problems they are where a first derivative chart is probably useful. Yeah.
Would you also be able to reason out that because 100 is a maximum and the critical value, it would have to be so that W would have to be 50 instead of restrictions?
Sure. I'll just paraphrase what you've said, Liam, so that it's on the video and everybody can hear it. If I understand you right, can you reason out that since you did question A and the maximum occurred when W was 50, that means that the area was increasing up to W equals 100. I think I just said W equals 50 in A, but I meant 100. In A, the maximum area corresponds to W equals 100, so the area is increasing as we go to W equals 100. And since 50 is before 100, it must be increasing up to 50 as well. Is that a fair summation of what you said? Yeah, certainly. And you know, to be honest here, this part B and the idea of having to reason it out or use a chart is mostly a post-secondary idea. Like you might encounter it here as a useful tool, but it's not usually that necessary. I will finish this by saying I've already told you that if you're given a max-min problem and you only have one mathematically legitimate critical value, then that's the one that gives you the answer. So we could have just stopped, we could have just stopped right here and said, since there's only one critical value, that's it. We didn't need to justify it. All right, I do want to move on here. We have a couple more questions that we want to look at, and then we will have lots of time tomorrow to go over more problems. And we will have some time today to go over more problems if you like. So we have 2 more examples to go, number 4 and number 5. Number 4 says that we have a cylindrical can that's going to hold 384 milliliters of soup. This question is very, very closely connected to your assignment 4B. But it's a little bit different, and I'll tell you why when the time is right. Find the dimensions of the can that would minimize the cost of materials. So I could make a can that was very, well, you know what? I have these. I think I have these diagrams because this is how we opened the lesson. Right? I mean, the volume of these 3 cans is not 384, it's 30. But I can make a can that holds a volume of 30. By the way, a cubic centimeter is a milliliter, essentially. I can make a can that holds a particular volume, and I can make it very tall and very narrow. Or I can make a can that is very short and very wide. Or I can make a can that's kind of just right, kind of a Goldilocks can, where that can in the middle, if it's just right, will not use much material. But the wider I make the can, the more material I waste on the top, even though I'm using less for the sides. And you can imagine that this would be the case if I made a can that was a kilometer in diameter. The fact that the height of the can is going to be a fraction of a micron doesn't change the fact that the lids are going to cost you a fortune. Okay? And that's what this problem is about. How can we just get back to where I was? How can we design the can to minimize the cost of materials? So the first thing I want to point out to you is you minimize the cost by minimizing the materials, right? So the less material you need, the less expensive it is. And what this really then is representative of is the area, the surface area. We run into a problem, and we're going to have this problem in the next example as well, where it's not really the area you're paying for, it's the amount of metal. There's a thickness to the metal. But if we make an assumption, and it's reasonable to make here, if we make the assumption that the thickness of the lid and the thickness of the bottom and the thickness of the sides are all the same, then the area is representative of the cost. So let's come up with a formula for the area of a can, the surface area of a can. Well, you can go to your formula sheet if you like, and you can see that it's 2 pi r squared plus 2 pi RH. But there is a reason for this, and I want to explain this to you now. Because in post-secondary, you're probably not going to be given a formula on an exam for a cylinder. If you take a can, and I actually had a can that I tore apart one time, and then one day I cut my hand on it, so I threw it out. If you have a can, and you cut off the top of the can, then it's going to be a circle. And if you cut off the bottom of the can, it's going to be a circle. So you remove the lid, and the top, and you have 2 circles. Well, the area of each of these is pi r squared. So we know how we could find the area of the lid and the bottom of the can. If you take this and you cut it here and then unwrap it, you're going to have a rectangle. You can imagine this just, going to somebody's cupboards and, as a prank, take all the labels off the cans. Right? It's a good prank, by the way. But if you take the label off neatly by cutting it down the center, I'm not suggesting you do that. If you cut the label down a vertical line across some point on the circumference and you pull the label off, it's going to be a rectangle. And when you unwrap this rectangle, when you unwrap it, you're going to have a rectangle where one dimension of the rectangle will be the height of the can, and the other is going to be the circumference of the can. Because this length here that I'm going to highlight is the distance around the can, which is circumference. So the length times the width for the label, or for the horizontal, not horizontal, the length times the width for the side of the can would be 2 pi RH, length times width, plus the 2 pi r squared. So that's where this comes from. Of course, that's not a good thing, having an extra variable, so we have to get rid of h. We're going to get rid of h by knowing that the volume is 384 cubic centimeters. Again, a cubic centimeter is a milliliter. That's our constraint. Our equation of constraint will be 384 equals pi r squared h, because that's how you find the volume of a can. You take the area of the bottom and multiply by the height. And that formula as well is on your formula sheet. So if I rearrange that for h, I get h equals 384 over pi r squared. And, you know, this is not really a particularly difficult question. It isn't. But it's one that you have to see in action before you can do it on your own. So the surface area of the can will be 2 pi r squared plus 2 pi r times h, which is 384 over pi r squared. So I've just done a substitution of this in here for h. Any questions to that point? All right, so let's simplify it. Of course, the golden rule is simplify before you differentiate. A equals 2 pi r squared plus, let's see, 2 times 384 is 768. Yep. So plus 768. What else happens here? The pi on the top cancels with the pi on the bottom. And we have r on the top and r squared on the bottom. R divided by r squared is 1 over r. Or, to prime this so that we can differentiate it sensibly, r over r squared is r to the negative 1. So this is the formula for the surface area of the can, which represents the amount of material in terms of the radius of the can. Now let's differentiate. dA dr equals 4 pi r to the 1. This pi is just a number. It's not a variable. There's no need to use any kind of product rule here. You're just wrapping that 2 around the r, and then you'll get 2 times 2 pi, which is 4 pi. R stays the same because it's the base, and you drop 1 from the exponent. Minus 768 r to the negative 2. Again, I'm just applying the power rule there. Now I can factor. I'm always factoring, right? You don't want to set this equal to 0 and try to rearrange it. That's a mistake. How do I factor this? Well, I'm pretty sure that 4 divides into 768. And I know that I can factor out r because there's r in each term, and I factor out the lowest exponent. I think the 4 goes into 768 192 times. I'm seeing a few nods, 192. So this will be minus 192 over here. And we've factored out r to the negative 2, so that's gone. Zebi, we're left with a pi here. Can you tell me what the exponent on r is going to be? Excellent. And that's the conversation we had this morning. Remember that. So I end up with pi r cubed minus 192, which means dA dr in its purest form, which is all factored with no negative exponents, is 4 multiplied by pi r cubed minus 192 on the top, and then on the bottom r squared. And you know, everybody, I go under the assumption here that the work that you can see on the screen here going from the top left down to the bottom left, all of that work is something that is not new. We've learned how to do that in the first unit, and you've gotten better and better at it as time has gone by. What are our critical values of r? Our critical values of r are 0 for the bottom, which I feel as though I've just wasted energy writing that down because we're going to throw it out. R is a radius. And then I'm just curious, how many of you see the other critical number without doing any real work is the cube root of 192 over pi? This is a case where, as much as I say, well, you just look at it and you know, sometimes what the brain requires is for you to look at it and go, well, you know what? I'm going to write this down and set it equal to 0 and rearrange it. It's not always a good idea. But in this case, I think it is. So I add 192 to both sides. I divide both sides by pi. And that takes me to this statement, because then I have to take the cube root of 192. Brain is a mysterious thing. I don't know why I wrote the number 2 there, because I'm pretty sure I said pi. But I have to take the cube root of 192 over pi. 0 is a nonsensical answer in terms of radius. In other words, it's not in the domain. The radius has to be greater than 0. So this is the optimal radius. This is the radius of the can that will minimize the amount of material. Now, we wanted to know the dimensions. So we know the radius is the cube root of 192 over pi. Now we have to find the height. And I've changed a lot over the years in a certain regard here. I used to be very hard line about this and say, well, what was h? H was 384 over pi r squared, right? That's our equation of constraint. H equals 384 over pi r squared. And I used to be very hard line about it and say, you want an exact value. But I don't, over the years, I don't know, maybe I'm softening. I've questioned what's so important about having to take this and simplify it. I just don't know what the value is in that at a high school level. I could go through it, but quite frankly, it's going to eat up 10 minutes of our time. And when push comes to shove next year, if you want an exact value, you're going to have to figure it out. But I don't think that's the important part of my job anymore here at this point. I'm not saying it's not important. I'm not saying I'm not willing to show it to you if you want me to. I'm just saying I don't think it's that big of a deal. So what we can do instead, well, we can do one of two things. We could just write this as our answer for h, and I'd be fine with that. Or we can go to decimal, which we probably want anyway. Which means what you would probably do here, everybody, is you would calculate r. Let's calculate it. I need to take 192 divided by pi. And I need to take the cube root. I'm just a fractional exponent kind of guy. I would raise this to the 0.3 repeating because I know a cube root is raised to a third. If you want to use the cube root function on your calculator, you can. If you want to say raised to instead, if you want to take the answer raised to bracket 1 over 3, that's another way you could calculate the cube root. Anyway, we get 3.94 centimeters. And if you want to find the height, now we can take that number and put it into h equals 384 over pi r squared. Of course, I hope everybody understands why this will not give me the right answer. I need brackets around the pi r squared. Otherwise, it's going to divide by pi and then multiply by r squared. Or if you're like me, I do that. I need to take this 384, I need to divide by pi, and I need to divide by r squared. So I get 7.9. 7.88 centimeters. It's interesting that that appears to be twice the radius. And in fact, I believe it is. If we were to simplify this expression, you might gain some inkling as to why it's twice. Now, just a couple of comments here about this question before we do the final example today. 384 milliliters is a typical soup can. If you go home, you grab a soup can, like a Campbell soup can out of the fridge, just a regular size one, and you measure it, that's not correct. It's not what they have. And the reason for that is the cost of the material for the lid and the bottom are different than the cost of the material for the top and for the side. And that's what assignment 4B is about. And you're going to have to take that into account somehow. And when the time is right, I will help you out with that, but not right now. Any questions with that example? Okay. I could easily give you an exam style question where, I mean, if you know the height is going to be twice the radius, I can give you one where there's no lid. Manufacture a cylindrical container with no lid. What dimensions would it have to minimize the cost of materials? In which case, that would be your formula. A equals pi r squared for the bottom plus 2 pi rh for the sides. Anyway, I don't want to go too far afield here. Let's move on to the next question. Student government is going to build a rectangular hall on the shore of Lake Fred. And I'm gonna just draw this for the time being. We're going to add a lot to this, and there's a lot more detail to what's going on. But this is the hall. All right. And there is a lake. I don't know where the lake is. Let's just say Lake Fred. Lake Fred is here. They want the wall that faces Lake Fred to be made of glass. And the other 3 walls to be made of brick. And the glass wall is more expensive. It says the cost per square foot. And here's where things get really iffy, because we're talking about cost per square foot, but we're not seeing the area of the wall. This is very, very difficult to conceptualize. We're talking here about this wall, which is glass, and the cost per square foot is 3 times the cost per square foot of all of the other stuff, which is made out of brick. When I talk about the cost per square foot, and I have to think here because I want to be able to show this on the camera as well. If and this is for the people in the room, so if you're looking on camera, you might not appreciate what I'm talking about just yet. This is the wall. And we're looking, everybody, on my diagram. You're just looking at this, right? This is the wall, though. So it's not the cost per foot of wall, it's the cost per square foot of the wall. But, and I'm going to get to you guys in Buck Mountain in a second, but assuming that the hall has walls that are all the same thickness and the same height, then if I tell you that it's 3 times as much per square foot, then it's 3 times as much per foot of wall. Because each foot of wall is going to be a certain amount of area of the wall. So on the diagram, what the diagram is showing, that's the top of the wall that you're seeing on the diagram, but this is actually the wall that you're talking about. And all I'm getting at is if I tell you that per square foot of this is 3 times as much for the glass as the brick, if all the walls are the same height and same thickness, then the cost of a foot of this wall lengthwise is going to be 3 times as much as the cost of a foot of the brick. Does that kind of ring true to you? Does that kind of make sense? We could, I'll maybe show everybody a different way of looking at this in a second, which is more algebraic. But the bottom line is, you're going to see problems like this from time to time, and you don't want to overthink them. You just want to say that means that the material for this wall is 3 times as expensive. So I'm going to use the word C here, or the letter C, for the thing we want to minimize. And here's where we get a little creative, because I'm not actually going to be coming up with a formula for the cost, because I don't know how much it is per square foot. But if I were to write out the length of all of this, this would be, what would this be? This would be W, this would be W, this would be length, and this would be length. So if I said, what is the perimeter? I'll go with perimeter here. The perimeter, well, maybe we'll back up. What are we trying to minimize or maximize? The cost. Do you agree that the longer the walls are, the greater the cost is? In other words, the cost is related to the perimeter because it's so much per foot of wall. So the perimeter would be W plus W plus L plus L. That would be the perimeter. And I realize I didn't write perimeter. I'm not done yet. In order to make this representative of the cost, I have to do that. I have to imagine, this is a good way of thinking of it, that glass wall of length L, I have to imagine I'm paying for 3 of the brick walls. So there's 3 of those L's. And this then becomes the equation connecting the thing you want to minimize to some other variables, but we have too many variables. Well, how can we get rid of one of those variables of L or of W? I'm going to give everybody a second here to read the question a little more carefully. Farhan?
Well, wouldn't we use the area to find the smallest perimeter first?
Can I ask how you would do that? The response was, could we use the area to find the smallest perimeter?
Yeah, I remember doing questions like those and reading what
What I would say to you is every question can be different, so be very careful about drawing any kind of strategies that rely on recognition. Oh, this is like that other problem. I'm going to do what I did in that other problem. There's something here that's very general that I've said you always want to use to eliminate a variable if you need to, and it's the constraint. What's the constraint here? Evan? Right, the area has to be 200 square feet. So you can have it 10 by 20 or 2 by 100 or 1 by 200, but the area, the length times the width, must be equal to 200. So we can rearrange that equation of constraint for, I don't think it really matters here. Let's rearrange it for W this time. W in that equation of constraint will be 200 over L. So we're going to get cost equals 2 times 200 over L plus 4L. So again, what I'm doing here, just to make sure that you understand, is I'm taking W, which is 200 over L, and I'm putting it in here. To get that equation. So now we can simplify it, we can differentiate it, we could be done. So cost equals 400 L to the negative 1 plus 4L. Again, you don't want variables in the denominator of something that you're going to differentiate. You want it in the numerator to make your job easier. So d cost, dl, and again, I'm using cost, but it's not really the cost. I did say that I would show you how you could actually include the cost in it, and I will do so in a bit for those that are interested. Okay. This will be negative 400 L to the negative 2 plus 4. So we factor out I'm going to go with a negative 4 L to the negative 2. You don't have to factor out the negative. I think, Arden, you and I were talking about that yesterday or the day before, or last week maybe. I like taking out the negative. Here we're going to get 100 minus L. Well, just a second here. We take negative 4 out of 4. We're left with negative 1. We're taking L to the negative 2 out of L to the 0. Zebby, I don't mean to put you on the spot, but can you tell me what L will be raised to in the brackets? 2, good. I just wanted to check because you did have that question this morning. I wanted to make sure that my explanation worked. We can certainly express this in a slightly different form. dCdl equals negative 4, and then we can go 10 plus L, 10 minus L over L squared. I would have hoped that many of you could look at this and say L equals 10 and negative 10 without physically having to factor it. But if you factor it, there it is. So what do we get for critical values of L? We get positive 10, we get negative 10, and we get 0 for the denominator. Wouldn't be much of a haul if the length of the haul was nothing. And I don't quite know what it means to say the length of the haul is going to be negative, which means there's only one critical value for L, which means there is only, that's the answer. That's what it means. Well, not that it's the answer. That leads us to the answer. So when L is 10, what were we in, feet? When L is 10 feet, the cost of the project is going to be as small as possible. So L will be 10 feet. I think I've cluttered things up enough. L is equal to 10 feet. The width is equal to, there are a number of ways for you to figure out the width, but I believe it's going to be 20 feet, and I'm just going with length times width equals 200. That's what I'm doing. You could certainly go to your equation of constraint and put L in as 10, and you'd have 200 over 10, and you'd get 20. So these are the dimensions that would give the minimum cost. So, and by the way, I want you to understand, maximizing or minimizing things isn't always the way it works out. You don't always want it to be this way, because this hall then would be very long and the wall facing the lake would be quite small, which maybe defeats the purpose of having glass. And what's the solution to that? The solution to that is the committee goes to principal and says, can you donate $5,000? We want more glass. I mean, the solution might be a practical one rather than a mathematical one. Any questions with number 5? Yeah.
Okay, so you're basically trying to find the smallest perimeter because that would be the smallest cost, right?
No, because the walls cost different amounts.
But
Right.
if it costs the same, then you just take the square.
You would, yeah, if they were to cost the same, then what we would have had here would be perimeter equals 2W plus 2L. I'll give you an extreme situation. What if the glass cost a million times, it was a million times more expensive than the brick? Then you understand that you want to start to make that glass smaller to minimize the cost. Any other questions with number 5? Okay, so let me show you the list of problems. On page 190, 12 and 16, 196, 7 and 8, 199, number 4. Can you just double check? Are these the ones typed out in your handout? Okay. Additional challenge problems. I don't believe this is included in your handout, but you can write them down right now. Please do write them down because I'm going to go away from this screen in a bit. When I say challenge, they're only challenged because I wouldn't ask them of you in this course, but man, the instant you learn about optimization in calculus and post-secondary, these are going to be assigned to you, these types of problems. Among others, they're not always that difficult. So what I would like to do, now that you've got that written down, is I'd like to let you get to work, but I did say that I would show you how you could do this in a more, I guess I want to say clinical way. And I'm going to point out to you, if you're interested, if not, you can get to work. I'm going to point out to you the reason why I don't start with this explanation. Every time I teach this course and I get to this example or an example like it, I go, I really should just do it this way that I'm going to show you because it's more correct. And then the next time around I try it, and students don't get it as well. Okay? What we're going to do, this is a wall we're looking at now. I'm going to draw a wall. And I'm going to wait for my computer to catch up. What we're going to do is we're going to assign a number for the cost per square foot of the wall. Okay? And the cost per square foot of the wall. So this is actually, maybe what I will do is, I'll make it a little bit bigger. This is a wall. This is not a top-down view of the hall. Okay? And what I'm going to do is say that the walls have a height of h, and I'm going to say that 1 square foot costs P dollars. I don't know why I'm using P. I didn't want to use C. I'm just using a letter. But before I go on, this could be a brick wall, this could be a glass wall. H is a constant, it's a number. The height of all the walls is 8 feet or 10 feet. It doesn't matter what the height is. And P is a constant. But I need to be specific here, so maybe I better do this. This is a brick wall we're looking at. So the cost per square foot of brick wall is P dollars. Okay? So now if I wanted the actual cost, I would have to take, and this is where it gets confusing, and I understand why I don't want to start off my explanation this way. Now I'm going to go back to the hall. This is the hall. Okay? And this is L, this is brick. This is W, it's brick. This is L, it's glass. And this is W, it's brick. And I am actually going to come up with a formula for the cost. It's going to be the cost this time, truly. So how would I find the cost of, let's say that this is this wall. And again, you understand that this wall here is being represented this way here. Okay. How would I find the cost? Well, since it's P dollars per square foot, I would have to take P and multiply by the area of that wall in square feet. And the area of that wall would be LH. You with me? Okay, let's move on to this wall. Well, I would have to take for that wall, and that wall, if I collapsed it or, tipped it over, would look like that. This would be the height, and this is W. So the area of that wall is W times H times P dollars per square foot. And there are two of those walls. There's one on the other side. Now I still have the glass one. Don't normally like to run an equation onto the second line, but I want to leave this diagram up here. We have the glass one. So this glass wall, again, if I tipped it down, if I just pushed on the wall here while the foot of the wall stayed there and it just fell, assuming the glass didn't shatter. This is L and this is H. So the area of that wall is LH. And then we need to multiply it by the cost per square foot. So LH, but the cost per square foot is 3P. Let's simplify this. Well, it pretty much is, but I want to rewrite it. Well, I think I can get rid of this. You're not writing it down, but if you want to look at it, you can go to the video that I'll post later. My cost is going to be PLH plus 2 PWH plus 3 PLH. Well, I have PLHs that can be added together. Yeah. To get 4 PLH, and I'm going to finish this, plus 2 PWH. Some of you might see a connection between that, which I'm just going to freeze on the right screen, and this. Except my clumsy attempt to explain why we can not worry about the height of the wall and the thickness of the wall and all of that is no longer needed when you look at the right screen. Right? It's no longer needed here. Now, I will admit, we are still not talking about the width of the wall. But that's because the cost was given as a cost per square foot, which would include the thickness of the wall. So where do we go from here? Where is it we go from here? Well, we can differentiate. But we need to get rid of a variable. I want to point out something to you that's crucial to being able to solve this now. Those are all constants. The cost per square foot of the hall, P, is what it is. $5 per square foot of brick. 3P would be 15, but the 3 is there somewhere. It's buried in there now. H is what it is. What's the how tall do you want the walls? Let's make them 12 feet tall. Because we want to put up a little storage area up top or something. P and H are constants and 4 and 2 are constants. So I'm going to rewrite this as cost equals 4PHL plus 2PHW. This is a variable, and that is a variable. We have too many variables. We still need to get rid of one. I don't think I need to go through the explanation of this again. Right, that was our result from the equation of constraint. So when I put that in for W, I get 4PHL plus 2PH times 200 L to the negative 1. So I end up with cost equals 4PHL plus 400 PH to the negative PHL to the negative 1. I'm just curious here. How many of you see that what's going to happen is once you differentiate, all of these constants are going to be factored out, and they don't play a role with the critical values. In fact, you know what? I could factor them out here. And I could, again, I like the way some of this math fits together. I could go back to a rule of derivatives, which is the derivative of a constant times a function is the constant times the derivative of the function. Which means this constant is just going to tag along for the ride the whole way, but it doesn't play a role in any variation or variables. So now we can differentiate it. dC dL is 4pH minus 400 pH L to the negative 2. Again, this is just a coefficient. So what can I take out? I can take out a 4, a pH, an L to the negative 2, and get 1 minus 100, pardon me, L squared minus 100. It's coming together, right? It's the exact same result. This is what I want to do. I want to do it this way. But I know I lose, it's a tough problem no matter what. I lose more people though when I do it this way. I would probably say that if you were doing this in post-secondary, you would need to take this approach. Anyway, just to really put a cap on this problem, dC dL is 4 pH, which who cares, times L plus 10 times L minus 10 over L squared. You know, the P and H are still there, but they don't play a role. So L critical is still 100, is still 10, negative 10, and 0. Okay. So the plan is for the remainder of the class, you're working on some of these problems. Pick one or two and get at it. And some of you already are. And tomorrow we're just going over problems and working on more problems. If you feel that you've really got the knack here of this and you understand what's going on, feel free to go ahead and start some of the challenge problems, but I won't necessarily do them right away for you.